What's going on, everybody? Hope you're doing awesome. So in this video, I want to show you how to code k-nearest neighbor classifier from scratch in Python. And I'll show you multiple ways of doing it. First in the inefficient, the most intuitive way, and then also in the more vectorized way for that ultra efficient implementation. So without further ado, let's get right into the code. First of all, we want to import numpy as np. We want to just declare our class k-nearest neighbor. Then let's just do some skeleton code of how the code is going to look like. We're going to have init. We're going to send in k. Oh, and I'll assume that you kind of know how k-nearest neighbor works in the intuitive way, and this is more of the how you would do it. Then we're going to have train self x and y. We're going to send in our data x and then the target class for each data point. Predict, and then we're just going to send in some x test. Then we're going to have compute distance, and then lastly we're going to have, let's see, define predict labels, and then we're just going to have if name equals main, and we're going to run the k-nearest neighbor from here. All right, so the train part is pretty easy. So the training part of k-nearest neighbor is just loading the entire data into memory. And yeah, let's do the init as well. Self.k is k. And let's see here. So what we want to do in a prediction, we want to call compute distance. And here we're going to send in x test. So let's do here x test like that. Then, so we compute the distances, right? For each example in our test data, we want to check what is the distance to every point in the training data. So that's what we do with the compute dist. And then we want to do, let's see here, we want to do return self.predict labels. So after computing those distances, we want to, for each example, we want to check, well, what are the k closest ones? And what is the majority class of those k closest ones? So let's do the compute distance first. Let's just do, let's see here. Yeah, so we're going to do it in the, as I said, the naive, inefficient way first. So we're going to do num, let's see, we're going to do num test, and we're going to do just to check the shape. And then num train is going to be self.xtrain.shape of 0. And then let's just define the distances to be np.zeros of shape num test and num train. So each row is a test example, and then each column is the distance to that specific training example. So the naive way is just iterating through each test example, and then each training example, and then just doing distances of I to j. So the distance between test example I and training example j, we're going to compute the Euclidean distance. So we're going to do np.square root of np.sum of x test. Let's see, x test, right, like this. And then minus self.xtrain j to all. And what I'm doing here is that I'm looking at the ith test example and then all of the features, and then the jth training example and all of the features. Let's see, we're going to do this squared right here, like this. We're going to take the sum like this. I think that's correct. Yeah. All right, great. And then at the end, we want to just return the distances. Now let's see. So we have done the compute distance, and now we want to actually, when we have the distances, we want to find what are the closest ones. And so what is the majority class for each? What is the majority class for the closest k points to each test example? And that's our prediction. So here we want to do num test. Let's do distances shape 0, right? Because distances will be the number of training test examples and then number of training example as the columns. So we can do y prediction to be np.zeros of num test, because we want the prediction for, let's see, we want the prediction for each single test example. Now we're going to iterate through. So we're going to do for I in range and num test. First thing we're going to do is we're going to look at the indices. So we want to find what are the indices for the distances which are the smallest distance. So we're going to use np.arg sort. We're going to np.arg of distances of I to all. And this will be the y indices. So essentially, let's see, maybe I should show you an example of this. Let's say we have distances, and let's say we would have, I don't know, 1, 5, -3, and then -10, something like this. Import numpy as np. And then, so the shortest distance here, this is just a single test example, right? And this is the distances to all 4 training examples. If we do np.arg sort of distances, we get back this right here, which says that the third index, so this one, is the one that is closest, right? Maybe this doesn't make too much sense because the distance can't be negative, but you get the point, right? We just look which one is the smallest of those, and that's the one we get first in our arg sort. Then what we're going to do is we're going to do k closest classes. We're going to check in ytrain for those specific y indices, right? And then we're going to do just to self.k, because we don't want the entire training data. We just want k points. And then we're going to do as type int, right? So now we get an array here of k classes rather, that are the closest to that specific test example. Then we're just going to do y prediction of that test example is we're going to count np bin count of k closest classes. So what this does is it counts how many times each class was in that array. So let's do an example again. Let's do classes are np.array, and then let's say we have the classes 1, 1, 3, 4, and 3 again, and then let's say do another 3, right? So we can see here that the majority is 3, right? And then the class 1 is the second most frequent. If we do np.bin count of classes, we see here that, okay, for the 0th class, okay, it starts from 0. The 0 class has 0 in it, right? In this array. Then the first class has 2 that is of that class. Second class is 0, and then the third class we have 3 of the third class, right? So what we can do is we can take np.argmax of np.bin count of classes, and we'll see that 3 is the most frequent one. That's exactly what we want, right? That's our prediction for that specific class. All right, great. So now let's just return ypred. And yeah, that should be it. What we want to do now is we just want to, I have some example data. You can download it from my GitHub if you want to follow exact. So we're going to do x is np.load txt, and I'll show on the screen how the data looks like. Example data, it's just in another folder. We're going to load that, and then the limiter is a comma. And then y will be np.load txt, and then pretty much the same thing, except targets.txt. All right, now let's see, invalid syntax. Yeah, there should be a parenthesis here. Then let's do knn is k nearest neighbor. Now let's do, I don't know, k equals 3. And first we're gonna train. So we're gonna do knn.train. Remember, this training part is just loading the entire data. And then we want to do y prediction. Y prediction is knn.predict of x. And so you would normally have some training data and some test data, and you would send them in sort of separate. But we're just going to do the prediction on the exact same data. And then let's also do, so let's do print accuracy. And then let's do, so sum of y pred equals y, and then divide by y.shape of 0, just to get some sort of accuracy of our model. Let's run this and we get some error. Let's see what it is. Yeah, it should be np.argmax as we did, and then bin count. All right, but I actually know that that's not correct for this one. We should get 93 if I remember correctly. All right, so I think I found the mistake right here. We don't want to take the sum and then square it. We want to square everything and then take the sum. Yeah, so that should be more like it. Let's see if this works. Yeah, and then we get 92%, and that should be correct for this data. All right, as I said, so this is the intuitive, the inefficient. You don't want to do this, but if you just want to gain an understanding of it, this is fine. But let's improve on this. So let's do, this is using 2 loops. And then in the prediction here, we're going to do number of loops. And let's say it's 2 by default. And so we're going to do if num loops is equal to 2. Then let's do what we just did and self.compute distance 2 loops. And then let's do if num loops is 1. Then let's do pretty much the same thing, but we're going to change this to 1 loop, right? And we haven't implemented this yet, but let's start. So let's define compute distance 1 loop, and then self and x test. All right, so we want to use some sort of vectorization to be able to do this. And what we can do is we can first define num test similarly as we have done here, this, and then we can just remove the outer loop. So let's do for I in range of num test. Okay, so now what we need to do is we need to compute the distance from a specific test example to all of our training examples at the same time in a single line. So the way to do this is we can do distances of I to all. Right, before we did distances from I for a specific ij. Now we do I to all, and then we're going to do np.square root, and then we're going to do np.sum, so pretty much the same right here. And then we're going to do self.xtrain minus xtest of I to all, and we're going to square this. And let's see, so we don't make the same mistake. So we're going to do another parenthesis here, and then like this. Okay, so what this does, this shape is, let's say, actually, let's see, print x.shape. So x is 90 by 2. We have 90 examples and we have 2-dimensional data. And this x test I comma all is just 1 comma 2. So when we subtract those, we're going to, for each training example point, we're going to subtract our current test example point, right? And then since we square, so NumPy does this broadcasting, which it subtracts for each row when the rows don't match, and it's going to do it for each row. Yeah, so yeah, I think that should be clear. And then one thing we need to do also is that we want to sum for axis equals 1. Let's see if that's, yeah, so axis equals 1, right? Because we want to subtract for all of the features, right, using the Euclidean distance, and then we want to sum all of the features and then square root of that, and we do that for each training example in parallel. All right, great. Let's then return distances, and now in the predict here, let's do num loops equals 2, and let's run that, and we get 93. Let's change it to num loop equals 1, and we don't get the correct thing. Okay, let's see. Yeah, so we want to, let's see, we want to close this parenthesis right here, And then we want to sum using axis 1, and then we want to close that parenthesis, and then we want to close the square root parenthesis right here. And then that should work. Yeah, so we get the exact same result as using 2 loops as we did with 1. And now what we want to do is we want to do the, as I said in the beginning, the ultra efficient, the fully vectorized version. So we're going to do another function right here. We're going to define compute distance and then vectorized. I'm going to send in the same thing. And let's do a pass on this right now. And then let's do else if, and then let's do else. We're going to do run distances is one loop, and then we're going to change this to vectorized. Okay. And let's see here. So actually, I want to go through how this works before I actually do it. So remember that what we want to do to compute train minus test squared, right? Let's say we do this for a single vector, or just remember if those were 2 variables, we can expand on this square operation. So we can do, this is train squared minus 2 train times test, and then plus test squared. Okay, this is just using the formula. If we expand this, and it works the same way with vectors. So let's say we actually do train equals np.random.rand. Then let's do 1 comma. Let's say we have a single example. Let's say we have 4 features, and we have test, which is also a single one, 1 comma 4. And then we have number examples is train.shape of 0. And let's then train on, I'll comment this one. Let's just use the one we did here, the random ones. And we're going to train using train. And we're going to just send in numpy.zeros of, let's say, num examples. Yeah, and that's it. And then we're going to predict on test. Say like this. Y is not defined. Yeah, so this print here, right? We'll just remove that as well. Yeah, so what we want to do, actually, let's do, just to make it a little bit clearer later on, let's do test minus train. And let's just reverse these ones like this. And same thing here then. Like this. Okay, so if we do that, let's just do test distance. So we're actually just distance is np.square root, and then we're going to do np.sum of test and then element wise squared, right? That's this part. And we want to sum axis equals 1, and let's do keep dims equals true, just so that numpy doesn't change the dimensions of it. When we sum to 1, we won't get shape like 1 comma like this. We'll get shape 1 by 1. So that's just what it does. And then let's see, we want to plus np.sum of train. So I'm doing this part right now. Train squared, and then keep dims equals true. And then let's move this a little bit, and then axis equals 1. And then let's do minus 2 times np.sum of test and element-wise train. So this is just a dot product, element-wise, and then we sum it. So let us compute the distance with the 2-loop version and call this the correct distance. And then let's compute the difference between this correct distance and this distance we just computed, and take the sort of the difference and then sum them. And hopefully this should then be a very, very small value if the implementation is correct. And then, as we can see here, there seems to be something wrong. So let's find the error. Yeah, so again, we get some sort of error here. We need to have right here, should have it like this. And then we should close it. Yeah, so it's just a parenthesis. Unexpected, yeah, so we don't have num loops when we do the get distance. All right, so what we get here is that there's actually no difference, which means that this is the same as doing the 2-loop version. All right, So it works when we have, so I mean this formula right here, it works when we have two vectors. But let's say we have, I don't know, if train was 10 examples instead. And what we want to do is this part, we're going to change this part to do -2 and then np dot of test and then train dot transpose. And why we do this is because, remember, we want each example in our train, all the features to be multiplied and added with all of the test features, right? And if we do that for all of the examples, then we would have, in this case, 10, I guess 1 by 10, right? So if we do test 1 by 4 times 4 by 10, because that's train transpose, then in the end we get 1 by 10. Okay, so the shapes add up and it does what we want it to do. It multiplies all the features in the test by all the features in the train, and it does so for all of the examples. Right, let's now check if that works. Yeah, okay, so we get an error, and first of all, let's do axis 1 right here, right, just to keep it symmetric. And then when we do keep dims equals true, remember that this part right here will be a 10 by 1, but as we said, this part right here will be a 1 by 10, and we want to add them, so we need to do transpose on this just to be able to add the dimensions. And yeah, so we're using broadcasting here again on this one, since this will be a 1 by 1, it will be added to each, all 10 of them. Try to implement this now in the general way. Let's remove this right here, and let's bring this back, and let's do this again, x, y, and dot predict of x, and then y pred, and then remove. So we just go back to what we had. Now we want to implement this compute distance vectorized, right? We're going to do sx test squared, right? So if we actually write that again, we do x test minus x train squared, x test squared minus 2 times x test times x train plus x train squared. So this is the formula. We just need to change this up a little bit so that we use the broadcasting from NumPy in the correct way, as well as having the correct shapes. So we're going to do first np.sum of x test element wise, and then axis equals 1, keep dims equals true. X train squared is going to be np.sum of x train squared, axis equals 1, keep dims equals true. And then the last, I guess, tricky part is the 2x test x train, which will be np.x test self.x train dot transpose. And then we just want to return np.square root of self dot x test squared, and then minus 2 times this right here, and then plus x train squared, and that transpose just as we did before. Then let's see, what I actually did in my implementation is I did self.eps, and then I added a small error term right here. Let's see, in all of the square roots, I just added self.eps, and I did that for all of the square root ones. I don't think it's actually necessary, but yeah, just to make it more numerically stable if there would be something very, very close to 0 for some reason. And let's see here, xtrain. Yeah, we can't use xtrain, we need to use self.xtrain. And yeah, that should be it. So this is a very, very compact formula. And then, yeah, so let's do it now with num loops equals 0, and let's see if we get back to correct result. And we do. So that's awesome. Now we did a very, very general k-nearest neighbor classifier, and you can sort of choose which one you want to use. Of course, the vectorize is going to be fastest. 1 loop is pretty fast, and then 2 loops, don't use that. Yeah, but that's it. Thank you so much for watching the video, and I hope to see you in the next one.